the screen now. Is this visible, students? Types of superconductors. Is this visible?
Yes, sir.
Yes, sir. Yes.
Okay. So, depending on the nature and the diamagnetic response of a superconductor, the superconductors are generally classified as the type 1 superconductors or soft superconductors. And the second, they are type 2 superconductors or the hard superconductors. So, the superconductors are classified as type 1 superconductors, type 2 superconductors. The same are also known as soft superconductors and hard superconductors. And you should not get confused, because in ferromagnetic materials also you have soft magnetic materials and the hard magnetic materials. And in main exam generally we observe that many students will get confused. Describe types of superconductors. Generally they write the properties of the soft and hard magnetic materials. Suppose that question is given. Describe types of ferromagnetic materials. They write the type 1 magnetic materials and type 2 magnetic materials. Both are different. So you should remember this. And superconductors, they are classified as a type 1 superconductors or soft superconductors. And the second category, type 2 superconductors, which are also known as hard superconductors. So coming to the first type, so a superconductor which exhibits a complete Meissner effect or perfect diamagnetism is called type 1 superconductor. That means yesterday we have studied the Meissner effect when a superconducting material cooled below its transition temperature is placed in a small low uniform magnetic field. It expels the magnetic lines of force. It excludes the magnetic flux density and it behaves as a perfect diamagnetic substance. This is called as Meissner effect. So a superconductor which completely follows this Meissner effect is called as a type 1 superconductor or soft superconductor. Some disturbance is coming. That is, below critical field, the superconductor, it excludes all magnetic lines of force and behave as a diamagnetic material. That means you take a superconducting material and you apply magnetic field. So as the magnetic field increases, then the superconductor starts excluding magnetic lines of force. So it behaves as a diamagnetic substance. It excludes all magnetic lines of force. So this continues up to the value of magnetic field, which is critical magnetic field. So when the value of applied field reaches critical magnetic field, up to that it excludes all magnetic lines of force and obeys complete Meissner effect, and it is a diamagnetic substance. When the value of applied magnetic field reaches the critical field, then what happens? Suddenly the material loses its superconductivity drastically, completely, and it behaves as a normal conductor. So this type of material, only two stages are possible. A abrupt change from superconducting state to normal conducting state happens for a soft superconductor or type 1 superconductor. So these are the materials which obey a complete Meissner effect or perfect diamagnetism. That is, below critical field, it excludes all magnetic lines of force and behaves as a perfect superconductor, and above critical field it loses its superconductivity completely and it becomes a normal conductor. If you take the diagram, see the superconductor along x-axis applied field and along y-axis it is the induced magnetic field in the opposite direction. Initially when you increase the applied field, then what happens? The magnetic flux, it also goes in the opposite direction but increases. So it increases like that. So when the applied field reaches the value Hc, which is called as critical field, then what happens? It stops and it loses its superconductivity completely. It becomes a normal conductor. So the superconducting state is up to Hc. So up to this field, it excludes all magnetic lines of force. It obeys Meissner effect and it acts as a perfect diamagnetic substance. And at the critical field and above critical field, drastically, it becomes a normal conducting material. These materials are called as soft superconductors or type 1 superconductors. Example, aluminum, zinc, mercury, strontium, all these are examples of these type 1 superconductors. So, want to write down this sentence. Type 1 superconductors are the materials Type 1 superconductors are the materials which obey Type 1 superconductors are the materials which obey a complete Meissner effect, or perfect diamagnetism. A complete Meissner effect or perfect diamagnetism. Below critical field, it excludes all magnetic lines of force. Below critical field, it excludes all magnetic lines of force and obeys Meissner effect completely. Meissner effect. Meissner also sometimes is called Meissner effect. MEISS, Meissner effect completely. That is, it acts as a perfect diamagnetic substance. A perfect diamagnetic substance. At critical field and above critical field, the material loses its superconducting property. Material loses its superconducting property and behaves as a normal conductor. These are also known as soft superconductors. You take the graph. Along x-axis applied field HA and along y-axis induced magnetic field HB. You can take where HA is applied magnetic field, HB is magnetic induction field grows in the opposite direction because it expels the magnetic lines of force, applied magnetic lines of force. Up to HC, it excludes all magnetic lines of force and it behaves as a superconductor obeying Meissner effect, and it is a perfect diamagnetic. At a HC, the superconductivity can be completely destroyed and it becomes a normal conductor. Aluminium, zinc, mercury, etc. are the examples of type 1 superconductors. Is it clear, girls? Only two states are possible. Superconducting state and normal state. Up to HC, it excludes all magnetic lines of force. It is a diamagnetic substance. It repels the magnetic lines and it obeys Meissner effect. And at a HC, the superconductivity can be destroyed completely and it behaves as a normal conductor. These are called as type 1 superconductors or soft superconductors. Then you take the heading type 2 superconductors. And you please take this diagram, graph. So if you take this type 2 or hot superconductors, in these materials, an intermediate state is available. That means whenever a superconducting material cooled below its transition temperature is placed in the magnetic field, initially the superconductor excludes the magnetic lines of force. It repels the magnetic lines of force. It continues up to a value Hc1, which is called as lower critical field. That means up to Hc1, it is a perfect superconductor. It obeys Meissner effect and it expels all magnetic lines of force. It acts as a perfect diamagnetic. And at Hc1, it starts to penetrate the specimen. So in this state, a stage starts where slowly it is losing superconducting behavior and gaining electrical behavior. So this combined state is continued up to Hc2, which is called as upper critical field. So at Hc1, the material starts to penetrate the specimen, and this penetration continues up to Hc2. Between Hc1 and Hc2, the superconductor is in a mixed state, obeying both superconducting and electrical conducting behavior. Hc1 is called as lower critical field, and Hc2 is called as upper critical field. When the value of upper critical field goes beyond this Hc2, then the material loses its superconductivity completely and it behaves as a normal conductor. These materials are called as type 2 superconductors or hard superconductors. And this mixed region, this is called as vortex region, where the material possesses both electrical and superconducting properties. So many alloys, they come under this type 2 materials or hard superconductors, niobium, titanium, niobium, zirconium are some examples of this type. In the previous case, only two stages are possible. Up to critical field, it is a perfect superconductor, obeys Masonry effect, and it expels all magnetic lines of force. At Hc1 and above Hc2, it is a normal conductor. Whereas in type 2 superconductors, an intermediate state is available, which is called as the mixed state or vortex region. So when a superconductor of this type is subject to external magnetic field, initially it excludes all magnetic lines of force. It is a perfect superconductor and it obeys Masonry effect completely. And this is up to a value Hc1 of the applied field. Hc1 is called as lower critical field. So once the applied field reaches this value, then the material starts to penetrate the specimen, and this penetration continues up to Hc2. So here, slowly, a partial superconducting behavior and a partial electrical behavior is observed for the material, which is called as vortex region or combined region or mixed region. So here, the material simultaneously will be a superconductor as well as a normal conductor. When the value of applied field reaches Hc2, which is called as upper critical field, then the superconducting behavior completely reduced, becomes zero, and it becomes a normal conductor. These materials are called as type 2 superconductors or hard superconductors. So this is type 2 superconductors. Is it okay? Students, did you got this? The difference between type 1 and type 2, boys? Please respond.
Yes, sir.
Yeah. And you should draw this diagram also for both cases. Type 1 superconductors and type 2 superconductors. And the tabular column, it is given. Just I'll read this. So type 1 superconductors, they exhibit complete Masonry effect. Type 2 superconductors, they do not exhibit complete Masonry effect because after Hc1, it is in a mixed mode. And type 1 superconductors, they show perfect diamagnetic behavior. They don't show perfect diamagnetic behavior. And in this type 1 superconductor, they have only one critical magnetic field Hc. Below that, it is a superconductor. Above that, it is a normal conductor. Whereas in type 2, they have two critical magnetic fields, Hc1 lower critical field and Hc2 upper critical field. So in type 1 superconductor, there is no mixed state or intermediate state. Either it is a superconductor or a normal conductor. Whereas in type 2, a mixed state or intermediate state is possible. It possesses both superconducting and electrical conducting properties. And here in type 1 superconductors, it loses magnetization abruptly. When the value of applied field reaches to Hc1, it loses its superconductivity abruptly and becomes a normal conductor. Whereas in this type 2 material, there is an intermediate state. Initially, Hc1 partially loses its superconductivity, but up to Hc2, it is in a mixed state. After Hc2 only, upper critical field, it loses its superconductivity completely. So an intermediate state permits the material to behave as a superconductor. And the type 2 superconductors are also called as soft superconductors. Type 2 superconductors are called as hard superconductors. And the examples are given here. What I have explained with the diagram previously, the same is represented in this tabular column. So these points you should write. Describe type 1 and type 2 superconductors. Generally, you will be getting for 4 marks or 5 marks. With the diagram, what actually type 1 superconductor and how it obeys Masonry effect, critical field, then how it is using superconducting state. With examples you should write. Similarly, for type 2 also, this intermediate state you should represent in the exam. So this you may get for 3 to 4 marks definitely every year. Shall I proceed for the next topic? Students, girls,
Yes, sir.
this Sinema will share the notes, otherwise you take the screenshot. Next, this is an important theory which is called as BCS theory of superconductivity. Take the heading BCS theory of superconductivity. So, superconductivity generally is an abnormal behavior because the material without any electrical resistance, how it continues the current is a little bit hypothetical initially, but it is practically quite possible. It is observed for many materials when they cool to very low temperature. So what actually permits the material, because not even each and every material when cooled to absolute zero temperature may not be a superconductor. Only certain materials they follow, they exhibit superconductivity. So what actually permits these materials so that the electrical resistance becomes zero? Many theories are introduced. Among a popular theory is BCS theory. BCS, it is a combination of three scientists. So this theory was forward by Bardeen, Cooper, and Schrieffer in 1957. This theory, popularly known as the BCS theory, this explains how a superconducting material at low temperature exhibits superconductivity without any electrical resistance is in a broad way explained by BCS theory. Actually, it is a complicated research paper by taking these matrices and also the chronic Fermi model, everything, the behavior of the conduction electron at very low temperature is explained. But as per our syllabus is concerned, only the gist, what are the features of this BCS theory we have to discuss. So in general, in a normal material, ordinary material or ordinary metal, the electrical resistance is because of the collision between conduction electrons and vibrations of lattice ions. So if you take any ionic crystal or any crystal surface, in that the ions are fixed in a periodic way that we have discussed in crystallography. They vibrate from their mean position, which are simple harmonic in motion. And these vibrations are called as phonons, which are quantized. So even though you take a crystalline surface, millions of ions are there, and each ion vibrates from its mean position executing simple harmonic motion, which is quantized. This vibration of lattice ion, this is called as a phonon. So whenever a conduction electron is traveling in a crystalline surface, there exists a collision between conduction electron and vibration of this lattice ion, that is phonon. An interaction occurs between the conduction electron and the phonon. During this process, some amount of energy for the electron is imparted to the lattice ion. That means electron will be losing some of its energy to the lattice ion. So with less energy only, the electron will be traveling the crystal surface and coming as an output. This is electrical resistance. How much input current actually you have, number of electrons per unit area actually when they are entering the surface, they may not be as it is when they leave the surface because some amount of this energy is absorbed by these phonons, which is expressed in generally as in terms of electrical resistance. This generally happens in ordinary material. But according to BCS theory, in a superconducting state, below transition temperature, that means at very low temperature, when the material is cooled to very low temperature, below transition temperature, then the electron travel in pairs rather than individually. This pair of electrons are called as Cooper pairs. Generally, it is against the principle because two electrons will not come closer because they are like charges. So they won't come. But surprisingly, in the superconducting state, below transition temperature, it is observed that the electrons travel in pairs rather than individually. So this pair, it was introduced by Cooper. So this pair of electrons, these are called as Cooper pairs. So these Cooper pairs, they move through the lattice without any scattering. So without any distraction, without any loss of energy, these Cooper pairs, they travel in the boundaries of the given crystal. And below transition temperature, an electron moving through the lattice close to the positive ion site a mutual attraction occurs between the electron and phonon due to Coulomb attraction. Lattice ion is positive in nature, electron is negative. So whenever a Cooper pair is moving, first electron, it is a pair of electrons, first electron, it is some mutual attraction occurs between the first electron and the phonon due to Coulomb attraction. So the first electron is interacts with the phonon. Then, so because of this, the ion core set into motion. So whenever the electron interacts with the ion set into motion. So this motion distorts the lattice. When ion vibrates extra, actually this vibrating from its mean position because of the interaction with the electron, it gets distorted, it's set into motion, and this distorts the lattice, giving rise to a wave of except positive charge that attracts another electron of equal spin in the opposite momentum. Actually, this happens at very low temperature. So one electron interacts with the phonon and it loses its energy to the phonon. Because of that, phonon gets distorted. But to get stability, again, the energy of the phonon is given back to the second electron. So what is the effective loss of energy of the Cooper pair? It is zero, because the first electron losing its energy to the phonon, the same energy again given back to the second one, so that the net loss of energy is zero, because with same momentum and also speed in the opposite direction, this wave, excess wave is imparted to the second electron. So the moment is transferred between the two electrons and via this lattice phonon. So you can assume that the electrons together form a Cooper pair, and known as this pair of electrons, this is called as Cooper electron. In the figure also you can see two electrons are coming, they interacting with each other, you can see. So one is disturbing the ion and the second one is giving back to the same second electron. In this way, without any much loss of energy, the electron is propagated in the crystal surface, so that the loss of energy is zero. Net loss of energy is zero in this case. So in this way, effectively, the electron is not scattered and moves through the material without any encountering any resistance. So this is the reason. Generally, what happens, electron traveling as an individual, this individual electron interacts with the lattice ion. Most of the electron energy is given to the ion, which is exposed in terms of electrical resistance. But in superconducting state at very low temperature, the electrons travel in pairs rather than individual, and this electron, first electron interacts with the phonon, it loses amount of energy to the phonon, so the phonon set into motion, so it distorts the lattice. So to get stability, the same energy is given back to the second electron. So an excess wave is created, because if in terms of wave nature only, this is again given back to the second electron with same momentum and the spin in the opposite direction. So effectively, the electron is not losing anything. In this way, it can be propagated throughout the crystal without any scattering. So this makes the electron to positive without any resistance, it can travel through the crystal, and this makes it possible to achieve high conductivity in the material. So this is at very low temperature, and in this case, when external electric field is established at very low temperature, it gives certain external electric field, then the Cooper electron gains additional kinetic energy and give rise to the current. So it generates only current, but it does not transfer this energy to the crystal lattice. So anyhow, this only supports the electron to move it to greater speed. So it gains additional kinetic energy, gains additional current only. It will not be losing its energy to the crystal lattice or phonon. So as a consequence of this, the material does not possess any electrical resistance and behaves as a superconductor. And remember, this is a prediction, and many metals and alloys can fit in Bcs theory, but not all. Still, research is going on. Some advanced materials, they may not obey this, but this is the most appropriate theory which could able to explain the superconducting behavior of materials at very low temperature. Is it clear? Shall I explain on this one? Students, is it a bouncer or could you able to understand something? Girls, shall I repeat this for 5 minutes? No response?
Yeah.
Repeat, sir.
Okay. Listen these points carefully. Whatever is required in these notes, as is you can represent. So in general, this Bcs theory explains the superconducting behavior of materials. Actually, scientists, we Barty and Cooper and Schaefer, they developed this model to explain the superconductivity at very low temperature. To take an ordinary metal, the ordinary metal, the electrical resistance is because of the collisions between the conduction electrons and the lattice ions. These lattice ions in a crystal generally they vibrate from their mean position, executing simple harmonic motion. The energy is quantized and these are called as the phonons. So conduction electron interacts with the phonon. So some amount of energy of the electron is given to the phonon, which is represented in terms of electrical resistance. So the input current is not same as the output current. But according to Bcs theory, in the superconducting state, below transition temperature, the electrons travel in pairs rather than individually, which is against to the Coulomb law of repulsion. Two electrons come closer at very low temperature for certain materials according to this prediction. So they travel in pairs, and this pair of electrons, these are called as Cooper pairs. And they move through the lattice without any scattering. Below transition temperature, suppose a Cooper pair is traveling in the crystal, first electron interacts with the phonon. So some amount of energy is given to the phonon because there exists a mutual attraction between the electron and the phonon due to Coulomb force of attraction. And because of this, the ion core is set into motion because it takes some energy. This motion distorts the lattice, so giving rise to a wave of excess positive charge. And this positive charge again given back to the another electron of equal spinning momentum. That is K1 is equal to minus K2, S1 is equal to minus S2. K1, K2 are momenta and S1, S2 are spins. So effectively, the first electron is losing its energy to the phonon. The same energy is given back to the second electron. So net loss of energy for the electron is zero. So in this sense, without any loss of energy, the electron is forwarded in the material. This process continues below transition temperature. So the momentum transferred between the two electrons and these two electrons get together form a Cooper pair and known as Cooper electron. So they are not scattered effectively below transition temperature because of this reason without encountering any resistance. Because effective loss is zero. This makes the material to achieve high conductivity. That's why it exhibits superconducting property. In addition to this, whenever external electric field is given, then the Cooper pair, Cooper electron gains energy, but it will not give this energy to the lattice. So as a consequence of this, without any loss of energy, with more energy, it is propagated in the crystal lattice. So it possesses, without the electrical resistance, it can be coming out as an output current. So it will not possess any electrical resistance and behaves as a superconductor. So these are the features of BCS. The mathematical proof is also there how electron wave can be propagated with the phonon, how it interacts with the phonon. But it is not required here as per first year BE is concerned. And these are the features of BCS theory you should understand. You should explain what actually the reason for electrical resistance, and in the superconducting state, how the Cooper pair will be behaving. This you should explain in BCS theory. Next, last one, last topic in this chapter, high temperature superconductors. No doubt, high temperature superconductors. And in brief, they are also called as HTSC. HTSC materials, high temperature superconducting materials. So the main challenge in the area of superconductivity is all superconducting materials are available at very low temperature, nearly equal to absolute zero temperature, that is minus 273 degrees centigrade. If you take pure mercury, it shows the superconductivity at a temperature 4.2 Kelvin, so almost is equal to zero. So first we should obtain the temperature, then only a material will become a superconducting material. So for many engineering applications, acquiring this temperature, very low temperature, is a challenge. So another field is again introduced, which is high temperature superconducting materials. So how the transition temperature can be enhanced so that at room temperature can we fabricate the superconducting films or materials is a challenge. And this branch of superconductors, this is called as high temperature superconductors or superconductivity. So in general, superconductors whose transition temperatures are generally more than 77 Kelvin are called as high temperature superconductor. Earlier 1960s only, this idea has been developed. So it is defined that generally materials which are having their transition temperature above 77 K or around 100 K are called as high temperature superconductors. In short form, they are called as HTSC compounds. And several new oxide superconductors just now late 80s or 90s, number of superconducting ribbons, superconducting metals have been prepared. Their transition temperatures are relatively very high, above 90 Kelvin. So temperature, you can say superconducting materials whose transition temperature generally more than 77 or 90 Kelvin is called as a high temperature superconductor. So these are ceramic materials basically, and they prepare from oxides of barium, copper, iridium, etc. All these transition metals. So the unit cell structure is crucial for the behaving as a superconductor for high transition temperatures. Okay, and these are the typical examples. Chemical formula, the transition temperatures of different alloys. You have to remember one to no need to take each and every one. Only for reference sake I have explained. So all these materials, their transition temperatures are above 70 in general. 111, 122, or they have little low transition temperature, but the above compounds they are having the transition temperature equal to above 90 or equal to 100 Kelvin. And in broad way, the high temperature superconductors are classified as 123 compounds, 124 compounds, cuprate superconductors, electron superconductors, and copper free oxide superconductors. Only the definition, only based on 123 compound, the remaining were also fabricated. So what actually 123 compound only definition is required as per your syllabus. So what are 123 compounds? So in 123 compounds, the unit cell of these contains one rare earth metal atom, two barium atoms, three copper atoms, and seven oxygen atoms. That's why these are called as 123 compounds. So in these compounds, the unit cell contains one rare earth metal atom, and two barium atoms, and three copper atoms. That's why it is 123, and oxygen is common, seven oxygen atoms. So these are called as 123 superconductors. So these superconductors, they form as layers of copper and oxygen atoms sandwiched between the layers of other elements in the compound. So copper oxygen combination, and how the whole generation, because here the dominant carriers are holes, because of whole movement, whole current, it is acting as a superconducting material. So copper oxygen layers are sandwiched between the barium and the rare earth metal, so that it permits the material to behave as a superconducting material. So you should write only this. The unit cell of 123 compound is consisting of one rare earth element, two barium atoms, three copper atoms, and seven oxygen atoms. You can see this structure also. Actually, this is the unit cell structure, and you can see the CuO planes or CuO chains in the material, supported by the remaining rare earth metal is yttrium. So the structure is yttrium, one yttrium atom, two barium atoms. The structure is Ba2, three copper atoms Cu3, and seven oxygen atoms. Symbolically, it is called as YbCO: yttrium, barium, copper, and oxygen. And these are the materials. This is the unit cell structure, and at below transition temperature, the electrical resistance is zero, and it behaves as a superconducting material. So this is 123 compound, and the second one is 124 compounds. So 124 compounds, same small change is there. In 123 compound, only one copper oxygen chain will be there. But in 124 compounds, the unit cell of these compounds contain two copper oxygen chains instead of one copper oxygen chain present in 123 compounds. These are still layered copper oxide materials, and these do not contain rare earth elements. So these are two changes. So rare earth element will not be present in these materials. Yttrium is there, and Y Ba2Cu4OA. Previously it is Cu3O7, but here it has a two copper oxygen chains, and rare earth element is not present. It is replaced by some another metal which is called element, which is yttrium here in this case. So these materials, these are called as 124 compounds. Just we should write what actually 124 compounds. And the third one is cuprate superconductors. So a cuprate superconductor, it has the composition like YBa2Ce3O7 with orthorhombic structure. Only unit cell can be modified at Taylor so that you can produce, fabricate a number of superconductors. A cuprate superconductor, it has a non-rare earth element, but the combination of one copper oxygen chain with orthorhombic structure. These materials are called as cuprate superconductors. Only should remember there is no concept to explain here. So the fourth one, electron superconductors. So in this, electrons are the majority carriers, and the parent cuprate has a tetragonal structure with the square planar Cu4 units. So only unit cell structure is crucial for deciding the superconducting behavior. The example is also given. So electron superconductors, electrons are the majority carriers. The electron current due to electron causes for the superconductivity. In the previous case, cold current is main reason for superconducting behavior. And finally, you have copper free oxide superconductors. So these are the compounds which are free from copper elements. In all the previous cases, copper is must, but some new alloys have been synthesized. In this, they are free from copper. So the examples are given here: lithium, titanium combination, barium, bismuth.
Visible, sir.
What am I?
Your presentation is not visible, sir.
Nothing is visible.
No, sir.
1 minute. Now is it visible?
No, sir.
Something happened. I'll check once. Again, we have started sharing the screen. Is it visible now?
Yes, sir, it's visible.
Some technical issue because data is transferred. Google maybe some because of that. Now it is visible now. So these are the compounds which are free from copper. Last one, lithium, titanium, oxygen combination like that. So in this way, the superconducting materials are classified into 1 to 3 compounds in which the unit cell is consisting of one rare earth element, 2 barium atoms, 3 copper atoms, and 7 oxygen atoms. This is the unit cell structure. And the copper oxygen chains are exactly sandwiched between the layers of other atoms. Holes are the majority carriers. Because one rare earth, 2 barium, and 3 copper atoms are there, it is called as 1 to 3 compounds. This little bit modified by another category which is 1 to 4 compounds. In this, you have 2 copper oxygen chains and rare earth element is not there. So why Ba2CO4OH is the example for this one. The third one is cuprate superconductors. So it is a composition like rare earth element with non-rare earth element with barium copper oxygen 1 to 3 compound, which is having orthorhombic structure. And the fourth one, electron superconductors. In these, electrons are the majority carriers, and it has a cuprate has a tetragonal structure with a square planar copper chains. And finally, some new materials have been synthesized which are free from copper, and these are called as copper free oxide superconductors. Like this, the high temperature superconductors are classified. It's not there in the syllabus, only for understanding sake. Generally, these are the 4 steps involved for the preparation of high temperature superconductors. Initially, the basic chemicals are mixed by using standard techniques. Then they can be put in high temperature for heat treatment, which is called as initial firing, so that a powder form or it gets stabilized with certain physical form, all these chemicals, and then intermediate firing is done. Some oxygen flow is allowed to pass the material, and also the carbon is removed from that. And finally, the final oxygen annealing is done. It's a very sophisticated process. Thin layers of these superconducting chips or superconducting ribbons or superconducting films can be prepared by this is the basic method, and for different materials, different techniques can be used. But these are the steps involved for the preparing the high temperature superconductor. The basic elements are taken in the required weight ratios, and they can be mixed by using standard techniques. Then with the initial firing, some physical form can be obtained. Then oxygen is allowed to pass through because copper oxygen tends to be formed in the material, which is called as intermediate firing and also called as oxygen annealing. And finally, again, it is treated for final oxygen annealing. So we will be getting a superconducting material with required physical form. These are the steps involved for the preparation of a high temperature superconductor. And applications of superconductor, there are many applications, mainly transmission. And generally in the conventional methods, 10 to 15% electricity is dissipated in resistive losses in transmission lines. So by using this superconducting transmission system, zero electrical resistance can be expected. So mainly in some countries, Germany and in US countries, superconducting fibers are there, but the challenge is main temperature maintenance. They have tried so that some 10 degrees or 11 degrees, some superconductors are available in certain standard conditions, and we can prepare superconducting fibers without electrical resistance. You can supply electricity. That is one main application. And second one is superconducting motors or generators could be made with a weight of because 1/10 of conventional devices, because the very less weight for the same output. It may be possible to build very large capacity generators for power plants. You can find in Google, power plants are there supported by the superconducting motors and generators, so that heavy high power can be produced, and the size is one-tenth of the conventional structure. So this is the advantage. And another application. And the next one is they respond for magnetic field. So superconducting magnetic energy storage stores electricity for long periods of time in superconducting coils because electrical resistance is zero. In the introductory part, we have the scientist has tested the resistance for 2.5 years. There is no change in the electrical resistance or conductivity. So you can store the energy. And in cancer treatment also, some superconducting materials are used so that the cancer cells can be reduced by high gradient method. That is also possible. So it can be used in magnetic storage and magnetic levitation, as we have discussed. It's a by using Meissner effect, you can bullet trains can be run with greater speed, and in the generation of high magnetic fields, in fast electrical switching, in squibs, this is another technique. Mm, in energy storage devices, because the electrical resistance is almost zero, and the important phenomenon is for making supercomputers and superconducting chips for space technology, for defense devices. You need this because for ISRO, for moving a satellite and taking the data and analyzing the data is a big challenge because number of satellites we are using, and they give some information that is taken within no time so that it can be analyzed, especially for weather reporting, everything. Ordinary computer cannot do that one. If you take a computer, supercomputer, it computes with no time, and immediately it will give. In 2004, after a Pokhran test, USA has denied to supply these cryogenic engines. So our scientists said we'll make these cryogenic engines, but for that you need a supercomputer. So that time National Physics Laboratory in IISc Bangalore, they come with certain formula and they have prepared a computer, supercomputer, which is called as a Param in those days. So the efficiency is 3 times greater than that time US computer, and the cost is 1/3 of the cost made by US. So still, this is a field China is competing for each and doing or fabricating hybrid fast superconductors, and India is also competing like that because which country has this supercomputer with maximum storage capacity and computing skills, and you can do wonders. So it is going on. Further, if electrical resistance is abruptly zero, then one computing calculation will be very speed, very fast. So superconducting chips and superconducting computers, it is a growing area. For that, you should take the good materials and composites. So which composite works? You should work on material science. Which composite can be used as a superconductor? For what application you can make it as a whether it is a superconducting film or superconducting layer or superconducting ribbon, whatever it's so. Still, the work is going on research in IICT in Hyderabad and Central University, Hyderabad University, and in many labs, what material will be more available there because there are many challenges. Temperature and also the electrical resistance is very close to zero. The consistency to be maintained for the material. So these are the challenges and work is going on. The only basic introduction of superconductivity we have discussed as per your first year level, but once you go to your MTech program or higher studies, probably once you have started working on these superconducting materials, definitely it is a growing area, you can say, what material will permit for the superconductor. So in this chapter, we have discussed what actually superconductivity, transition temperature, and what are the properties of superconductors, general properties of superconductors we have discussed, and the types of superconductors as type 1 and type 2 superconductors. Then we have discussed Bcs theory, features of Bcs theory, high temperature superconductivity and the classification of high temperature superconductors also we have discussed. And finally, few applications. If possible, some applications are given in YouTube video. I try to upload, not now, after some time. And I think by taking attendance, I'll stop. Any doubts in this superconductivity, students? There is no derivation at all, so you can do it very easily. Students, any doubt in this?
No, sir.
I'll share the PPT tomorrow probably to go through. If you have any doubts, you can ask. Okay, I'll take attendance now.
Sir, with this we completed unit 3 or it's
Unit 3 is completed.